In this problem, we're given that the greatest common divisor of m and n is 2. We want to prove that the Euler's totient of m and n equals to the 2 times Euler's totient of m times Euler's totient of n. So, to solve this problem, well, first we need to understand what is the Euler's totient function. So, to do this, we can take an example. Let's just take the Euler's totient of 10. Well, the Euler's totient of 10 we know that the Euler's totient of n equals to, it counts the numbers coprime to n up to n. So in this case, if you just write the numbers from 1 to 10, well, which of them are going to be coprime to 10? Well, they're going to be 1, 3, and 7, and 9. So it's going to be 4 of these numbers. So the Euler's totient is going to be 4. Once again, the Euler's totient means that it counts the number of positive integers up to n, which are relatively prime to n. So, with that out of the way, we can now solve this problem. To solve this problem, well, first, we can define m and n based on the GCD that m and n is equal to 2. Since the GCD is 2, we can write m equals to 2 to the power of a times k, and we can let n equal to 2 to the power of b times l, where GCD of k and 2 is equal to the GCD of l and 2 equals to 1. So, for example, k and l are odd. Also, we know that the minimum, or the GCD of a and b equals to 1. So this means that one of a or b must be 1. Without loss of generality, we can let b equal to 1. So we have n equals to 2l. And then m equals to 2 to the power of a times k, where a is greater than or equal to 1. From the GCD of 2 to the power of a times k and 2l equals to 2, we have 2 times GCD of 2 to the power of a minus 1 times k times l, and l equals to 2. This simplifies to the GCD of 2 to the power of a minus 1 times k, 2 to the power of a minus 1 times k, and l equals to 1. Since l is odd, l shares no common factors with 2 to the power of a minus 1. Thus, we have GCD of k and l equals to 1. So this means that k and l are coprime. Now, we can calculate the Euler's totient of m and n. Well, the Euler's totient of m and n equals to, of m times n, equals to the Euler's totient of 2 to the power of a times k times 2l, which equals to the Euler's totient of 2 to the power of a plus 1 times k times l. Since 2 to the power of a plus 1 is a power of 2, and k times l is odd because k and l are odd, we have the GCD of 2 to the power of a plus 1 and kl must equals to 1. Therefore, the Euler's totient of 2 to the power of a plus 1 times kl equals to, it must equal to the Euler's totient of those two products. So in other words, the Euler's totient of 2 to the power of a plus 1 times kl equals to the Euler's totient of 2 to the power of a plus 1 times the Euler's totient of KL. And then we know that the Euler's totient of 2 to the power of a plus 1 well, we know that this equals to 2 to the power of a plus 1 minus 2 to the power of a plus 1 minus 1 by property of Euler's totient equals to 2 to the power of a plus 1 minus 2 to the power of a equals to 2 to the power of a. Now, so we have the Euler's totient of m n equals to 2 to the power of a times the Euler's totient of KL. And then since they're coprime, we need to remember that this will mean that the Euler's totient of KL equals to the Euler's totient of K times the Euler's totient of L. Thus, we have the Euler's totient of Mn equals to 2 to the power of A times the Euler's totient of K times the Euler's totient of L. Now we need to fix that as 2 times the Euler's totient of M times the Euler's totient of N. Well, this will equal to the Euler's totient of M equals to, well, this will become 2 times the Euler's totient of 2 to the power of A times the Euler's totient of K. Because we know that M is 2 to the power of A times K. And then we'll have Euler's totient of N, which is equal to the Euler's totient of 2 times the Euler's totient of L. The Euler's totient of 2 is just going to be 1, so it becomes the Euler's totient of L. So then we see that this whole thing will equal to 2 times the Euler's totient of M, or in other words, this will equal to 2 to the power of A times the Euler's totient of K times the Euler's totient of L. So this will finally match up with here. So we have the result that the Euler's totient of M and N equals to 2 times the Euler's totient of M times Euler's totient of N. And the proof is complete.